Let's consider the titration of a strong acid, hydrochloric acid, with a strong base, sodium hydroxide. Let's say we have 20.00 milliliters of a 0.500 molar solution of hydrochloric acid in a flask. Into the burette, we place the titrant, which is a 0.500 molar solution of sodium hydroxide. Before we start the titration, we need to calculate the initial pH of the hydrochloric acid solution. Because hydrochloric acid is a strong acid, we assume it ionizes 100% in water, which means that all the HCl turns into H+ ions and Cl- ions. Therefore, if the concentration of HCl is 0.500, that's also the concentration of H+ ions and Cl- ions in solution. Since pH is equal to the negative log of the concentration of H+ ion, we take the negative log of 0.500, which gives us a pH equal to 0.301. Titrations can be represented by titration curves. For this titration, we put volume of sodium hydroxide added on the x-axis and pH on the y-axis. Since we haven't added any strong base yet, our first point is at 0 milliliters of base on the x-axis and a pH of 0.301 on the y-axis. Titrations can also be represented by particulate diagrams. Since we haven't added any of our base yet, the only ions present are H+ and Cl-. Since the concentration of H+ ions and Cl- are equal, the diagram has two particles of each ion. Next, we open the stopcock on the burette and allow some of the sodium hydroxide solution to go into the flask containing the hydrochloric acid. Let's say we add 10.00 milliliters of the 0.500 molar solution of sodium hydroxide. Because sodium hydroxide is a strong base, we assume that it dissociates 100%, which means that all of the NaOH turns into Na+ and OH-. Therefore, if the concentration of sodium hydroxide is 0.500, that's also the concentration of sodium ions and hydroxide ions in solution. Let's write an equation for the acid-base neutralization reaction that is occurring. An aqueous solution of sodium hydroxide reacts with an aqueous solution of hydrochloric acid to form water, and an aqueous solution of sodium chloride. The net ionic equation leaves out all of the ions that don't participate in the reaction. These ions are called spectator ions. Since sodium and chloride ions are present in solution both before and after the acid-base reaction, they are the spectator ions. Therefore, we can take out the spectator ions to give the net ionic equation of OH- plus H+ goes to H2O. To get another data point for the titration curve, we need to calculate the pH of our solution after adding 10.00 milliliters of base. We can figure out how many moles of hydroxide ions we have added by using the molarity equation. We added in 10.00 milliliters, or 0.01000 liters, of a 0.500 molar solution of sodium hydroxide. Since molarity is moles over liters, 0.500 is equal to the number of moles over 0.01000. Multiplying 0.500 by 0.01000 gives 0.00500 moles of hydroxide ions. We are now ready to set up an ICF table. I stands for initial moles, C stands for change in moles, and F stands for final moles. We start with the I row, and we plug in 0.00500 moles for the initial moles of hydroxide ions. Next, we need to find the initial moles of H+ ions before any base was added. Since we had 20.00 milliliters, or 0.0200 liters, of a 0.500 molar solution of hydrochloric acid, 0.500 is equal to the number of moles over 0.0200. Multiplying 0.500 by 0.0200 gives 0.0100 moles of H+ ions. Next, we can plug this number into the I row of the ICF table. To fill out the I row, we pretend we haven't formed any water yet, so we put a 0 under H2O. Now, we want to fill out the C row of our ICF table. Since we have many more moles of acid already present in our flask than the amount of base that gets added, we know that all of the hydroxide ions that get added will be neutralized. So, the change in hydroxide ions is equal to minus 0.00500 moles. All of the ions get consumed. Looking at the balanced equation, we can see that there is a 1-to-1 mole ratio between hydroxide ions and H+ ions. So, if we lose 0.00500 moles of hydroxide, we also lose 0.00500 moles of H+ ions. So, we put minus 0.00500 in the C row for H+ ions. Finally, the balanced equation shows a 1-to-1 mole ratio between hydroxide ions and water. So, for every mole of hydroxide ions that gets consumed, we produce a mole of water. Therefore, we get a plus 0.00500 moles in the C row below water. Since we start with 0.00500 moles of hydroxide and we lose 0.00500 moles, we're left with 0 moles of hydroxide ions. Since we start with 0.0100 moles of H+ ions and we lose 0.00500 moles, we are left with 0.0050 moles of H+ ions. To calculate the pH of the solution, we need to know the concentration of H+ ions in the solution. Since we started with 20.00 milliliters of hydrochloric acid solution and we added 10.00 milliliters of sodium hydroxide solution, the total volume is now 30.00 milliliters, or 0.03000 liters. To find the concentration of H+ ions, we take the final number of moles of H+ ions, which was 0.0050, and divide by the total volume of the solution, which is 0.03000 liters. 0.0050 divided by 0.03000 gives a concentration of H+ ions of 0.17 molar. To find the pH, we take the negative log of the concentration of H+ ions, which gives us a pH of 0.77. So, the next point on the titration curve is at 10.00 milliliters of sodium hydroxide added on the x-axis, and a pH of 0.77 on the y-axis. We can draw in a smooth line to connect the 2 points on the titration curve. Notice how the pH of the solution has increased. Let's also think about the particulate diagram at this point of the titration. Because the sodium hydroxide that was added neutralized half of the total acid that we had present in our solution, half of the acid should remain. So, if we add one Na plus and one OH-, the one OH- will react with one of the H+ ions to form water. Water is not shown in the particulate diagram for clarity. So, only one H+ ion remains in the solution. We also still have the 2 chloride ions that we started with, and the 1 Na+ ion that was added. Now, we continue the titration by adding another 10 milliliters of base to our solution. Since we've already added 10 milliliters, adding another 10 milliliters means that we've added a total of 20.00 milliliters of base. Since we started with 20.00 milliliters of hydrochloric acid, the total volume in our flask will be 40.00 milliliters. Let's first figure out how many moles of hydroxide ions we have added to the solution. The base has a concentration of 0.500 molar, and we've added a total of 20.00 milliliters, or 0.02000 liters. So, using the definition of molarity, we multiply 0.500 times 0.02000 to get a total of 0.0100 moles of hydroxide ions. Next, we need to know the initial number of moles of H+ ions in the solution. We've already calculated that there were 0.0100 moles of H+ ions present. So, at this point in the titration, we have added the same number of moles of hydroxide ions as the number of moles of H+ ions that were originally present. Because the moles of base are equal to the moles of acid, we've reached the equivalence point. Since H+ and OH- react in a 1-to-1 mole ratio to form water, all of the H+ and OH- ions are used up, which leaves only water. Because the pH of water is 7.00, the pH of the solution is now 7.00. So, for a strong acid, strong base titration, the pH at the equivalence point is 7.00. We can now add this point to our titration curve. So, after 20.00 milliliters of base added, the pH is equal to 7.00, and we've reached our equivalence point. If we were to graph all of the points in between this point and the previous one, we would see that the slope of the line increases dramatically as we get closer to the equivalence point. Looking at the particulate diagram, we've added one more sodium ion and one more hydroxide ion. The hydroxide ion reacts with the H+ ion present to form water. Since the hydroxide ion reacts with the last H+ ion, there are no more hydroxide ions or H+ ions present. However, we still have the two chloride ions that we started with, and the two sodium ions that came from adding sodium hydroxide. So, at the equivalence point, we have an aqueous solution of sodium chloride. Now, let's continue our titration. This time, we add only a very small amount of base, 0.20 milliliters, which brings us to a total of 20.20 milliliters of base added. Even though we have added only a very small amount of base, because there are no H+ ions to react with the OH-, the pH increases dramatically to 11.4. Going back to the titration curve, we find the point corresponding to 20.20 milliliters on the x-axis, and a pH of 11.4 on the y-axis. So, even though we're just past the equivalence point, the pH has risen dramatically. If we were to graph the rest of the titration curve, the pH continues to increase, but eventually levels off. For the particulate diagram, we can add in another sodium ion and a hydroxide ion. Since there are no H+ ions present to react with the hydroxide ion, we are past the equivalence point of the titration. Alright, as a quick recap. For the titration of a strong acid with a strong base, initially only the acid is present. As base is added, the pH slowly increases. When the number of moles of acid is equal to the moles of base added, the titration has reached the equivalence point. The titration curve shows us that the pH changes dramatically around the equivalence point. For a strong acid, strong base titration, the equivalence point occurs at a pH of 7.00.